So node architecture. First, let's see the outline of this lecture. Uh, for the node architecture in various sensor networks, we have a couple of subsystems. Like sensing system, right? For the sensing subsystem, we will cover this ADC in details. ADC, and another subsystem is a processing subsystem, or you can say processor subsystem. And here you can see that we have a couple of options for the processor subsystem in various sensor networks. For the processor, we can use microcontroller, we can use DSP, digital signal processor, ASIC, application specific integrated circuit, FPGA, field programmable gate array. So these are the options for the processor. But usually the most widely used one is microcontroller. Let me connect the pad so I can write some command here. Another subsystem actually is the communication subsystem, and you also can say it's the communication interface. Yeah. We know that this is also significant component, right? Yeah, because you know that in the sensor network, right? Each sensor node, they need to communicate to each other, and also within the sensor node, right? Subsystems, they also need to communicate to exchange data, right? Yeah, sometimes. Yeah. And here we are going to cover SPI, serial peripheral interface, I2C, inter-integrated circuit. So these two are the most important ones, most important communication interfaces. And actually we have another subsystem, which is the power supply, right? The power supply is the necessary essential component subsystem, right? Yeah, for various sensor node. But here actually we will not talk about too much about power supply subsystems. And at the end, we will introduce some prototypes about sensor nodes. Yeah. So one is the I-mode node architecture, XYZ node architecture, and this Hawk-Thorpe node architecture. Yeah, actually, there are some other node architectures. So later, when we talk about TinyOS in details, so I will introduce the popular sensor mode, and we will, maybe we will write another survey paper on those sensor nodes that are widely used and support TinyOS. Okay. All right. So for the wireless sensor nodes, they need to have these subsystems. They need to have these functions: sensing, right? Processing, and communication, right? Sensing, processing, communication. So here for the processing, Actually, in general, this processing means that process some simple, no, I mean some simple processing tasks. Like once the sensor get data, right, they can do a little bit pre-processing, right, the noise, right, filtering, such simple processing tasks. Okay, and maybe also you can do some like extract very simple information from data. Yeah, you know such simple tasks. It doesn't mean this processing like a PC, like a workstation does. Okay, it's not like that level processing. Because for wireless sensor networks, the sensor node, we know that the size is limited, right? Resources limited, and the microcontroller, uh, you know, it's not that powerful. So they cannot do deeper level processing work. Okay, so please be aware of this. So especially for centralized wireless sensor networks, why it's called centralized, right? All the sensor nodes, they will send the data to one station. Okay, yeah, and either that station is powerful enough to process all the data, or that station continue relay the data to a PC, to process. Okay, for decentralized wireless sensor networks, for that case, each sensor node will process the data by themselves, but the functions are limited. Yeah, the functions are limited. Okay, be aware of this. So communication, as I mentioned, between sensor nodes, among sensor nodes, they need to communicate, right? Yeah, to exchange data, exchange information. The data information is not limited to the sensory data, right? It also includes some information about sensor nodes themselves, right? What are the node ID, right? What are the locations, right? What are the uh, you know timers, right? The timers, the sensor node received a certain piece of data, right? So what are the timers? Yeah, such information they also need to exchange to communicate. And within the sensor node, itself, different subsystems they also need to communicate to, read data, right? To send instruction. Yeah. And for the power supply subsystem, we are not gonna talk about that much. Yeah. And here you also need to be aware that there is a balance trade-off between this flexibility and the efficiency, right? Yeah. So both in terms of energy and performance. Yeah. So because we cannot provide that powerful, resources, right? Yeah, including energy, including the processor, right? Yeah. So we cannot expect the wireless sensor node can do very powerful job, as what PC does. Yeah. Okay, this is general architecture of wireless sensor node. Yeah, you can see that here, the first part in this block, this is the sensor subsystem. Okay, and next block is the processor subsystem, and the third block is the communication subsystem. You can see in the sensor subsystem, here you can see we have different kinds of sensors, right? This is a light sensor, right? Accelerometer, temperature sensor, right? Humidity sensor, chemical sensor, pressure sensor, motion sensor, a mechanical sensor, every kinds of sensor, right? And connect to the sensors, the device is the ADC, analog to digital converter, yeah, ADC. And after ADC, so the signal, the data is converted from analog signal to digital signal, and then we can send the digital, signal, digital data to the processor subsystem, processor subsystem, and you can see the communication is realized through SPI, I2C communication interfaces, right? Yeah. And in the processor subsystem, here we have some instructions, right? Yeah, we have some data stored, right? We have some memory here. Yeah. And as mentioned, here we only do some simple processing tasks. And then between the processor subsystem and communication subsystem, right? So they need to exchange data. That is done through SPI. Yeah. And the data is sent to communication subsystem. And here in this subsystem, we have some other processor, coprocessor, and also have the unit for wireless communication. You can see that here we have receiver, transmitter. We can transmit the data out to other sensor node, right? We also can receive the data from other sensor node. Yeah. That's the function of the communication subsystem. Okay, so the table shows that for the sensing subsystem, right? So we have sensors, right? Yeah, and we have their application areas, and we have the sense they want, or signals, and also we have the explanations, to explain actually what quantity they can acquire. So here first accelerometer. Yeah. So this sensor is widely used in wearable wireless sensor networks, wearable wireless devices. Yeah, right. Yeah. Actually, on smartphone we have this accelerometer, right? Smartphone, Apple Watch, yeah, and some other wearable devices. Yeah. And it can be used in, you can see here, healthcare, right? This is the most widely used area. Yeah. And also like AVM, I say, I'm not sure what they represent, but the most widely used area is healthcare, sometimes transportation. And actually, the actual centimeter can sense the 2D or 3D, right? Two-dimensional or three-dimensional accelerations of movements of people or objects, right? Yeah. Like when we wear, some devices, wearable devices with accelerometer, right? When we move, either our body or our arm, right, or our legs, and then the movements will trigger the accelerometer, and it can get some signals about accelerations of our movements. Acoustic sensor. This is not that popular, right? So in our daily life, capacitance sensor, yeah, not. Okay, ECG, EEG, EMG. So these sensors are used in healthcare areas. So I'm not sure if you have the experience with these sensors. So actually, in hospitals, right? So sometimes, like, if you want to do some, do some diagnose, like you want to check your heart, right? If you want to check get some information about your brain, right? So we will stick some devices at the area around your heart, right? And also maybe you wear some stuff on your head, right? So those are these sensors, and they can detect some information about your heart and about your head. Yeah. So you can see here they can acquire the information like heart rate, right? Brain electrical activity, muscle activity. Yeah. So these are very widely used in healthcare areas. Electro sensors, gyroscope. Actually, usually gyroscope is used together with accelerometer. Yeah. In wearable devices, wearable wireless sensors. Humidity sensor. This one is a very common sensor that for weather environment monitoring applications. Yeah, right. With light sensor, with temperature sensor together. Yeah. And of course, it can measure the humidity in the environment. Infrasonic sensor, magnetic sensor, oximeter. So this one is also used in healthcare area. It can detect the blood oxygenation. Yeah. pH sensor, not that well known. Photoacoustic sensor, piezoelectric sensor, temperature sensor, yeah, very common sensor. Oxygen blood flow, yeah. So you can see here a lot of sensors actually are used in healthcare fields, right? And I also emphasize them because they are either closer to our real lives, or actually they have more important applications, right? Yeah. So for some others, I didn't mention that much. It's because they are not that widely used, or we don't have that much experience with that. Yeah. And here you can see there is another sensor, is passive infrared sensor. Yeah. So actually this one can detect the infrared radiation from objects. Yeah. So actually I use this kind of sensor a lot. So in my human sensing research, I use this sensor a lot. Yeah. So this sensor can use in healthcare area, also can use in monitoring area. Yeah. So like you want to monitoring some indoor environments, right? Offices, labs, right? So you can use this kind of sensor. ADC. Yeah. So ADC, the function is to convert the output of a sensor, which is analog signal, continuous value, into a digital signal, into a discrete value. Yeah. So why we do that? Because you know that in the nature, right? So the signals are all analog signals, right? And the sensors, they only can detect the analog signals. But for the processing purpose, right? So all the devices, right? 99% of the devices we used in daily lives are digital devices, right? Yeah. So these devices can only process digital signals. So we have to convert the analog signal to digital signals. Yeah. And during this conversion, there are two steps. One step is that we need to do quantization with the analog signal. Yeah. And what scale of the quantization, what level of quantization is needed, depends on the frequency and magnitude of the signal. Yeah. Also depends on the processing and the storage resources, of the processor. Yeah. Another is the sampling frequency. Yeah. We know that after the quantization, right, and we will do sampling, but what is the frequency or what is the sampling period, right? Because our purpose is to convert the analog signal to digital signal, right? But during this conversion, we don't want to lose, much information, right? If we lose too much information, the converted data may not reflect the original signal, right? And may not contain enough information for us to process, right? Yeah. So this sampling frequency is important. The sampling frequency, sampling period. So usually we use the Nyquist rate, as a base, to measure the sampling frequency. Yeah. But sometimes it doesn't suffice because of noise and the transmission error. Yeah. So maybe we need a frequency higher than this Nyquist rate. Yeah. But sometimes, for certain applications, like for the compressive sensing, right? A new term, for recent years, compressive sensing. It means that actually we can use, less sampling data to retrieve the original data. Yeah. So for that case, for that compressive sensing, we can use some, frequencies less than Nyquist rate, And the resolution of ADC, so you can see, is determined by this equation. So here, Q is the resolution, EPP, is the peak-to-peak analog voltage, peak-to-peak analog voltage, and is the resolution in bits, and the Q is the resolution in volt. Okay, the processor subsystem. This processor subsystem interconnects all the other subsystems and other peripherals. So the main purpose of processor subsystem is to execute instructions, right, pertaining to sensing, communication, and self-organization. Yeah, actually the processor subsystem is the brain, right? It's the brain of this sensor node. And this processor subsystem usually consists of a processor chip, non-volatile memory, an active memory, and internal clock. Architecture overview. So there are three basic computer architectures, can be used for very sensor node architecture. The first one is the von Neumann architecture, right? The second is the Harvard architecture. Third, super Harvard architecture. So these are the very, very basic architecture, because for very sensor node, right? So we know that we cannot expect where sensor node is that powerful as PC, right? So we cannot use complicated architectures to build the very sensor node. Yeah. So we have to use very simple, very basic architecture for them. So this is the von Neumann architecture. So in this architecture, it only provides a single memory space. Yeah. This memory space is used to store program instructions and data. Provides a single bus. It's used to transfer the data, right, between processor and memory. And it's in a slow processing speed. Yeah, slow processing speed. So this diagram shows the von Neumann architecture for very sensor node. So you can see a single memory, right? A single memory. Yeah. Harvard architecture. So this architecture is a little bit more complicated. So it provides a separate memory space to store program instruction and data. And each memory space is interfaced with a processor with a separate data bus. And so the program instructions and data can be accessed at the same time. And here it adopts a special single instruction, multiple data operation. Yeah. It supports multitasking, but doesn't provide virtual memory protection. Yeah, so you can see here, for this Harvard architecture, we have space for program memory. We have another memory space for data memory. They are separated, right? Yeah, separated. But they can be accessed at the same time. Super Harvard architecture. This is an extension of the Harvard architecture. So in this architecture, two components are added, right? This internal instruction cache, temporarily store frequently used instructions. Yeah. So for frequently used instructions, right? We usually store them in the cache, right? Yeah. Not only for this such a node, also for PCs, right? Yeah. We have a cache, as an internal component in the CPU, right? That is to store some instructions, frequently used instructions. In that way, we don't need to get the instruction from the main memory, many times, right? So it can save some time and increase processing speed, right? Yeah. And here, so we already talked about this cache, right? So here, for the cache, I would like to ask you a question. Why, uh, if we put the instructions in cache, and then why it can increase the processing speed? Or we say why the speed of the cache is faster than the main memory. So anyone can answer?
It's closest to the CPU, right?
Yes, it's actually is within the CPU. Yeah. Okay. Any other ideas? Any other answers? Why cache is faster? Okay. So like I mentioned, right? So it's within the CPU, so it's closer to the CPU, right? Yeah. So maybe, so from the architecture level, right? From the programming level, so you can say that, okay, because it's closer to the CPU, it's within the CPU, so that's why it's faster. Okay, yeah, this is from the architecture level, architecture perspective. But if we go to lower levels, go to the hardware composition level, yeah, the bottom level. If we consider the compositions of memory, the main memory, right, RAMs and the CPU and the cache, yeah, what are the differences from the composition? So we know that for the RAM, we have static RAM, we have dynamic RAM. Okay. Maybe let me write down. We have static, dynamic RAM. Yeah. So usually this dynamic RAM is used for the main memory. And this static RAM usually is used for cache. Yeah. And what are the differences for them? Yeah. For the static RAM, actually is composed of transistors. But for the static RAM, but for the dynamic RAM, right? So it's composed of a capacitor and one transistor. Yeah, I mean for each unit. Yeah, for each cell. Like for the static RAM cell, each cell is composed of 4 to 6 transistors, and for the dynamic RAM, each cell is composed of one capacitor and one transistor. Yeah, because the difference in the composition, they will have different speeds. Yeah. So for transistors, because there's no leaking problem, electron leaking problem, and there's no refresh operation, so it's faster. Yeah, it's faster. But with this capacitor, we know that the capacitor has a leaking problem, right? And it needs refresh operation. And it takes some time, right? So usually a couple of milliseconds. Although it's in milliseconds, it's very fast to us, right? But for CPU, millisecond counts, right? Yeah. So during that refresh operation, the refresh cycle is not accessible. So you cannot read any data from during that cycle. You have to wait. So that refresh operation will lower down the speed of this dynamic RAM. Yeah. So that's why dynamic RAM, DRAM, is slower than static RAM, SRAM. And usually this DRAM is used as main memory, and the static RAM is used as cache. So that's why cache is faster than main memory. Okay, so this is the essential reason why cache is faster than main memory. Okay, so in the future, if people ask you this question, I hope you can give them this answer from the lower hardware composition level, because this is the essential reason. So cache is closer to CPU, right? That is, yeah, you can say that is one reason, but that is not the essential reason. This is the essential reason. Okay. All right. This is RAM's cache. Yeah. So direct memory access, DMA. Okay. You can see here the difference is that it has one component within the processor, instruction cache, right? Instruction cache, and also another component, I/O controller. So this is an extension of Harvard architecture. Okay, so before we discuss different options of processor subsystem, let's Have a break for 5 minutes. Okay, let's continue. So for the processor subsystem, the major option is microcontroller. Okay, so here before we talk about microcontroller in details, first I would like to ask you a question. What is a microprocessor? What is a microprocessor? So anyone can give me an answer? So you should already have taken some courses, right? Computer architecture, right? You know, machine organization, right? What is a microprocessor?
Is it like a CPU?
Okay, yes. So a microprocessor actually is you know, processor on a single integrated circuit. Yeah. So you can simply understand it as a CPU. Yeah. Yeah. And here the key point is that okay, only the processor, right? You can see only the processor on an integrated circuit. And in comparison, what is a microcontroller? What is a microcontroller?
Would it be like um, microcontrollers are directing and sending the programs,
Uh,
kind of like conductors in a way, like do they tell what parts of the program to run?
uh, okay, I cannot clear, I cannot hear clearly. But yeah, so uh, you know, for microcontroller, you know, from the name you can tell a little bit, right? It's not a processor anymore, right? It's a controller, yeah. So actually, uh, it contains more components. So you know, it's still an integrated circuit. Besides the processor, it has fixed memory. Okay, it has fixed I/O peripherals. Yeah. Okay. So now you can see what are the differences, right? So a microcontroller actually is an integrated circuit that encapsulates processor, memory, I/O peripherals. Okay, but here, it's fixed size. Yeah, so fixed size. Yeah. So the memory, usually is very small. Yeah, very small. Okay, and the I/O peripherals are also limited. And for microprocessor, you can see, although it's also an integrated circuit, but just processor itself. Okay, this microprocessor is a computer processor on an integrated circuit, right? But for the microcontroller, you can see it have more components. So the processor core, right? Memory, yeah. But these memories are fixed size memory, okay? Yeah. Clock generator, I/O peripherals, yeah. And ADC, yeah. Sometimes ADC. So, what are the advantages for microcontroller for wireless sensor node? So, microcontroller is very suitable for building computationally less intensive standalone applications because of its compact construction. So, like I said, the memories, the I/O peripherals, they are fixed size. Yeah. So they are compact, small size, compact construction, low power consumption, low cost, and high speed of programming, easy debugging. Because we can use the high level programming language with microcontrollers. So actually for a microcontroller, you can think of it as a tiny computer, right? Tiny computer. Disadvantages, not that powerful, not that efficient as customized processors such as DSP and FPGA. We know that FPGA is very powerful, right? Yeah. And it can be FPGA is scalable. DSP is more efficient. Yeah, more efficient. DSP. So the main function of DSP is to process discrete signals, right, with digital filters, to process discrete values. So the filters minimize the effect of noise on a signal or enhance or modify the spectral characteristics of a signal. So the analog signal processing requires complex hardware components. Digital signal processor requires simple adders, multipliers, and delay circuits. So here is the emphasis. DSP are highly efficient. Most DSPs are designed with the hardware architecture. The advantages of DSPs are that is powerful, is efficient, It's useful for applications that require the deployment of nodes in harsh physical settings, like environment monitoring, right? Animal monitoring. Disadvantages. Some applications may require protocols that require periodical upgrade or modifications. And then the network should support flexibility in network reprogramming. But with DSP, it cannot do that. But with FPGA, like I said, FPGA is scalable. It's more flexible with FPGA. ASIC, application-specific integrated circuit. So ASIC is an IC, right? Integrated circuit that can be customized for specific application. Yeah. So here, from the name, you can see that it's application specific. So it's designed, particularly for one application or for few applications. So the functions are very limited. Yeah. So it's not flexible at all. It's not scalable, and so with a certain ASIC, you only can do this work. You cannot apply it to do other work. Yeah. Here are two types of ASICs. One is fully customized, and the other is half customized. So for the full customized ASIC, logic cells, circuits, or layout are custom made in order to optimize cell performance. Includes features which are not defined by the standard cell library, and is expensive and long design time. Because this needs to be customized, so the design time usually is longer. Half customized ASICs are built with logic cells that are available in the standard library. So for both cases, the final logic structure is configured by the end user. ASIC is cost-efficient solution, flexible and reusable. So reusable is. So here, cost-efficient actually, means the implementation cost. Doesn't mean the design cost. Actually, the design cost is very high, right? So from the price and from the design time, the cost is very high. But the implementation cost is low. Yeah, it's efficient. ASICs have these advantages that relative simple design, but the design time is longer. Can be optimized to meet a specific customer demand. Yeah. And it can incorporate multiple microprocessor cores and embedded software. Disadvantages: high design development costs, right? Lack of reconfigurability. So here the ASICs actually they are not to replace microcontrollers or DSPs. Actually, it's to complement microcontrollers and DSPs. FPGA. So actually, from the composition perspective, composition level, actually, FPGA and ASICs they have the same compositions with basic logic gate cells, right? The difference is that FPGA is more complex in design and more flexible to program, because ASICs are customized to a certain application, right? But FPGA is not. Yeah. So FPGA is more complex, more flexible. So the programming of FPGA is done with the support of circuit diagrams and hardware description language, VHDL or Verilog. Yeah. You can use these two hardware description languages to program FPGA. The advantages, FPGA has higher bandwidth, yeah, flexible in application, right? It's really programmable, really configurable. It supports parallel processing. It works with floating point representation. Yeah, more flexible. Disadvantages is that it's complex. The design and the realization process is costly. Yeah, and another thing is that the size of FPGA, because we usually expect the FPGA is very powerful, right? So with that expectation, the size of FPGA usually is bigger, yeah, because if you want to have a more powerful function, so you have to use much more transistors, yeah, transistors. So the size of FPGA usually is larger. Yeah. Okay, so let's stop here today. So we cover the sensing subsystem, the processor subsystem, and introduce four options for the processor subsystem. So any questions?
For the homework, the papers that you had assigned